Okay, so hey guys, how's it going? So this is going to be video 2 on my series on photon interactions. This video is going to be covering problems 8 through 14. So let's pick up where we had left off. So part A, what is Bremsstrahlung radiation? So Bremsstrahlung radiation is generated from an electron interacting with an atom. And there are two kinds, but the first kind is the dominant interaction, and that's from electron-nucleus interaction, or a negative positive charge. So this is the main Bremsstrahlung interaction. This is going to be an electron coming in. The nucleus charge is going to interact with an electron. It's going to provide a momentum change to the electron, and the momentum change to the electron is going to generate the Bremsstrahlung radiation. The second and less dominant interaction is from an electron-electron interaction, or a negative-negative charge. This form of Bremsstrahlung radiation creates terrestrial radiation in air. So part B, what factors increase Bremsstrahlung? So the electron-nucleus interaction is proportional to atomic number squared. The electron-electron, or second Bremsstrahlung interaction, is proportional just to atomic number. Other factors that increase Bremsstrahlung radiation are going to be energy of the electron and the thickness of the material, of course. So for part C, what does the shape of the spectrum look like? The Bremsstrahlung spectrum is triangular. Here's a depiction. With respect to this depiction, the energy of the incident electron is going to be 200 keV, and as you can see here, it's a spectrum all the way down to 0. In this particular case, the lower energies were filtered. This is characteristic radiation, and so forth. For part D, when do we use thin targets? So thin targets are typically used for the creation of high MV Bremsstrahlung beams, also known as transmission targets, and these are used in a LINAC. What is an example of a thin target? So, for example, the Electa Versa uses a 1 millimeter tungsten transmission target. For F, when do we use thick targets? So thick targets are primarily used in the creation of X-ray imaging, or KV. Here's a depiction of this is an electron coming off a filament, hitting a, say in this case, a tungsten target, and this is a reflection target. What's an example of a thick target? So in this example, usually tungsten for X-ray imaging. For mammography, typically molybdenum, but could also be tungsten. So for problem 9, we're going to be labeling these diagrams. First off, label the category, whether it's a heavy charged particle, neutron, electron, or photon. The first diagram. Oh, also these are percentage depth dose curves with respect to so PDD with respect to depth in water. So first depiction is photons. Second is electrons. Fourth is heavy charged particles. And the third is neutrons. Notice that the PDDs look somewhat similar for photons and neutrons. Neutrons are indirectly ionizing radiation also. So they share similarities. Now let's start to guess the energies for the different PDDs for photons. So starting from the first one, notice that the D max is less than 0.5. So I'd say it's less than 1 MeV. Looks like a smaller energy. So 100 kVp. Second one looks to be lower than 1 MeV. So it has a D max less than 0.5, 400 kVp. Third one looks around 0.5. I'd say cobalt 60. Yep, got that one. Fourth one, D max looks about 2.2. I'm going with 10 MV because it's a spectrum. Got that one. And the last one, around 20. All right, 22 MV. Let's move over to electrons. First one, let's say 10 MeV, and 9. Approximately 20 MeV, 18. Approximately 25 MeV. Oh yeah, 32 MeV. So generally, this is in water. You can take the maximum MeV for the electron, divided by 2, and you can get a approximation of the depth. So in this case, 9 MeV was approximately 5 cm. Should have guessed higher than 25 MeV. So 32 MeV is approximately 15 cm. So that's a good method of approximation. So I'll give the answers for neutrons because those are hard to approximate. So what should you get from this particular plot? I think that it is similar to photons. So if you get an answer, if you have to answer a question like this on a multiple choice exam, be careful knowing that the PDD versus depth for neutrons is similar to photons. DT tends to yield a high neutron energy. In this particular case, 16 MeV. So dB target lower. It produces a lower energy neutron. 62 MeV. It's gonna be proton on beryllium target. It produces a little bit higher, but I don't think these have to be memorized. I think that might be asking too much. Let's look at heavy charged particles. I won't guess the energies, but we are given the answers on the side, but that's okay. Okay, so notice that the 190 MeV protons tends to go the furthest in depth. We have 190 MeV deuterons, 310, so higher energy MeV carbon ions. Let's compare protons to deuterons. They have the same energy. Protons are one proton. Deuterons are 1 proton, 1 neutron. So it has a higher mass. So the collision stopping power, the mass can be found in the beta term of the collision stopping power formula. I will probably create a lecture focused only on charged particles. So I think I'll go in further depth at that particular moment. Carbon ions, which have a substantially higher mass, tend to go less than protons at a much higher energy. So notice that there is this Bragg peak. That's going to be as the, let's say for example, protons, as it goes further in depth, the energy starts to decrease. As the energy decreases, the collision stopping power goes way up. That's what the Bragg peak is. So moving on to problem 10. Some more review questions. What is pair production? Pair production is when a photon interacts with an atom, produces an electron-positron pair. What's the threshold for pair production? 1.022 MeV. C is a little bit of a tricky question. Could get you on an exam. Where does pair production occur? So typically with the Coulomb field of an atomic nucleus, but it can also occur with the Coulomb field of an electron. And this is typically known as triplet production, which brings me into question part D. Triplet production is when a photon interacts with the Coulomb field of an electron. The electron is ejected and becomes the third particle. What's the threshold for triplet production? It's 2.04 MeV. For F, what is the formula to calculate the average energy, given as kinetic energy, that the electron and positron would receive? So this is the average between the two. This is the formula. HV is the energy of the incident photon. For G, what is the formula to calculate the average angle shared between the electron and positron? So they do each have different angles, but this is how the formula to calculate the average angle between the two. Where MOC squared is the rest mass of the electron, so 0.511. And this is the average energy shared between the two. So moving on to problem 11. We're going to do example calculations with those two formulas. So from an incident photon of 10 MeV, calculate the average energy given to an electron-positron pair from a pair production interaction. So we have the initial photon energy. Sub it into that formula. Not too difficult. We get our answer of 4.489 MeV. For B, let's calculate the average angle between the positron-electron pair. Once again, let's utilize the formula. So, excuse me. So MOC squared, drink of water. So MOC squared is 0.511 MeV. I can utilize the average kinetic energy that we calculated and place that in. Now, watch out when you're performing this calculation with respect to your calculator. If it's in radians, you're going to have to then convert it radians to degrees, which is which can be performed by multiplying the radians answer by 360 degrees divided by 2 pi, just as a refresher. So moving on to part C, what is Rayleigh scattering? So Rayleigh scattering is when a photon interacts with atomic electrons, but there is no change in the photon energy. The photon trajectory does change, however. So, sort of running with Rayleigh scattering, essentially it's free scattering of the initial photon. So so what you want to know is, would this have an effect on film? So going into part D, what percent of low energy X-rays are Rayleigh? Less than 5% of a KV beam are Rayleigh. So not a huge impact on film. Now, part E, these types of questions are very common questions within medical physics, and sometimes they can throw you off if you just forget maybe they'll trick you and throw you off, and you could lose some points. So you do have to, I'd recommend performing a couple of these problems before going into a multiple choice exam. So here's a good example. So a 40 keV electron is incident on a material with binding energies in the K shell 30 keV, L 4 keV, and M 0.7 keV. What types of X-rays can be emitted from this interaction? So the answer is Bremsstrahlung. You get Bremsstrahlung radiation up to the maximum energy of the electron, so 40 keV. Now you can also get characteristic X-rays from the different shell binding energies, the orbital electrons. You could get the possibilities are 29.3 from 30 keV and 0.7, 26 from 30 and 4, and 3.3 from 4 and 0.7. So yeah, watch out for these kinds of questions. So moving on to problem 12. Part A, what is the formula for calculating the Thomson scattering coefficient? So there it is. Part B, what is the formula for calculating the Kleine-Scheine coefficient? So there it is. And most importantly, C, when can you use each formula? So you can use the Kleine-Scheine coefficient formula for all energies. Now the Thomson, which is the smaller formula, can only be used for low energies and when the incident photon energy approximates the scattered photon energy. A good rule of thumb when you can use Thomson would be, I would say typically around 0.01 MeV, around the low energy. Which brings us to D. Well, sorry, let me get back to that. So most of the time, so basically you're going to be using the Kleine-Scheine formula. So this could be a formula that you may want to memorize. Okay, so let's move on to D. Example calculation with them both. So calculate the differential cross-section using both the Thomson and Kleine-Scheine formulas for a photon of HV 0.01 MeV, scatter photon energy of 0.01 MeV, so they are approximate, and an angle of 0. So I can easily plug these in. So in the first case, I plug in 0. I get 1, 1 plus 1, 2, I cancel it out. I get just the radius of the electron. This is the electron radius squared. Let's perform the same calculation, but with the Kleine-Scheine formula. So HV prime over HV, 1 squared, 1, 1. And we end up getting 2 over 2. We can cancel it out again. And the answer is the electron radius squared once again. So this is good news. They're the same answer. So that's good. That means that the example was good. So here's a plot depicting differential Kleine-Scheine versus angle of scattered photons as a function of initial photon energy and the the different energies for the initial photon energy. And if we look at scattered angle being 0, we look at 0.01 MeV, we get the same answer, 7.94. So moving on to problem 13. How do you calculate, notice that in the other two formulas, we needed the scattering angle, right? But looking at problem 13a, how do you calculate the total cross-section for both Thomson and Kleine-Scheine formulas? So for all angles, not just those particular angles. So essentially what you do is you take the Thomson formula and the Kleine-Scheine formula, and you integrate both formulas with respect to all angles. So from 2 pi to 0 for B and pi to 0 for phi. I'm not going to perform the calculation. For Kleine-Scheine, it's about, I think, about a page long, and Thomson is about half a page. I think too, if that was on a test, the instructor would probably give you a heads up. So with respect to the total cross section for those formulas, moving on to B, for the low energy Thomson case, the answer is a constant. What is it? It ends up, after you integrate with respect to all angles, for the Thomson case, the low energy case, it goes to this constant. So this might be something to keep an eye on as a potential multiple choice question. For part C, what is the formula for calculating the total cross section for the Kleine-Scheine formula, or the high energy, for high energy photons? So this is with respect to all angles. We've integrated the Kleine-Scheine formula. What's a formula? It results in this formula where alpha is hv over mlc squared. I don't think you'll have to memorize this. Nice to see it though, so you can recognize it. Now moving on to part D. Just what does the total cross section mean? I kind of explained it, but and use an example. So the total cross section is the probability of a scattering event occurring when one photon passes through a layer of 1 electron per centimeter squared. So given an example, given 6.65 times 10 to the negative 25 centimeters squared per electron, if 10 to the 27 photons pass through this total cross section, 665 scattering events will occur. So it's the probability. Okay, so moving on to problem 14. In my last problem in my video on photon interactions, I have a very interesting problem, and I'll read it first and go through the diagram. So an X-ray point source emits monoenergetic 1 MeV photons on a low Z target. Compton scattered photons from Z, so these two Compton scattered photons, they hit both of these two pieces of lead, person 1 and person 2, and I want to know which person receives a lower radiation dose, person 1 or person 2. So why is this question so good? It's an excellent learning problem because you have to set up a ratio of dose between these two locations, but the problem doesn't give you like the fluence. It doesn't give you means to really calculate the fluence. Like you don't have the fluence rate, so you have to cleverly set up a ratio between the two. And I'll work through it and show you how it's done. So right off the bat, we're definitely going to need to know the scattered energies in each case. We're going to have to calculate an attenuation through each lead for, using each scattered energy. We're going to need the formula for collision kerma, and let's start working through it here. Okay, so here's our formula for the scattered photon, HV 1 plus HV prime. So let's go ahead and input the data for each scattered photon. So in this case, for the first scattered photon, it's 90 degrees plus 15 degrees, 105 degrees. So I plug that into the formula. For this case, for the second case, scattered photon, it's 90 minus 15, so 75 degrees. I'll plug that in and calculate for HV prime, and that's my answer. Okay, so we can now use the Klein-Ashina coefficient. We have the scattering angles. We have our HV prime, our HV. So this is very valuable for our case because we're going to be setting up a ratio for radiation dose. So we can input our values. And that's what I've done here for both cases. I've came to this result. R0 squared over 2. This is a constant. If you want, you could put in the values and calculate it, but it doesn't matter because we're going to cancel it out when we form a ratio. Okay, now we got to set up a ratio for radiation dose. Now collision kerma is equal to energy fluence over mu En over rho. And collision kerma is equal to dose. In this case, we're going to approximate CPE. So collision kerma is equal to dose if we approximate charge-particle equilibrium. We can use this formula. So we're going to have to approximate it. And this is just saying that we still need to calculate an attenuation for the lead in each case. Okay, so we're going to need a UEN over rho for tissue for each scattered photon. We're going to need a mu-En over rho for lead at each scattered photon energy. So I went ahead and gathered them. Here's the mu-En over rho for lead at this scattered energy. Mu-En over rho for tissue at this scattered energy at the first one. And then the same for the second. So now we'll go ahead and calculate the attenuation through each piece of lead. I'll probably also I'll probably end up creating a video on photon attenuation too later, so I won't go through it in extreme detail. But attenuation can be calculated by E, the exponent, minus mu-En over rho. This is the straight ahead approximation of lead multiplied by the density times the distance, x. So I did this for each case. I input each mu-En over rho for lead in each energy, and I was able to calculate the attenuation for each. So now I have the scattered energy. We're going to be putting this into our dose ratio because this is the energy fluence. So energy fluence can be broken down into energy and fluence. So I'll go ahead and show my ratio. So here's the differential Clanishina cross section for the first one, 0.220. Here's my attenuation through the first lead calculated right here. Here's my photon energy of the first one calculated and input. And here's my mu-En over rho for the tissue calculated at the first scattered energy. I do the same for the second part, and I reach my conclusion. So for the calculation, which person receives a lower radiation dose? The answer is the first person. Very nice calculation. In many instances in medical physics, when you're looking through textbooks, you're finding like calculations that are only really checking one concept, or two if you're lucky. In this case, you're checking many concepts, and questions like this are very, very hard to come by, and they're very valuable if you can understand all these concepts. But this is problem 14, and this is my last problem for my lecture on photon interactions. So I think I have put together a nice review on photon interactions in 2 videos. So with that, I'd like to thank you for viewing, and that's all. Bye.